What's that? That was vague enough that that actually is valid. They all share the same properties for volume. So by that token, we're saying, so the example that we used in class, which doesn't work because Tyler's not here, that I occupy the exact same volume as Greg. Is that valid?
No.
Okay. So why for gases is it all of a sudden different? Ultimately, it's not different. Okay. However, we simplify and we come up with the approximation that the distance between any two particles in a gas is so large that really none of the particles occupy any volume. So that assumption really holds true based off of our number one assumption. Gases are made up of such tiny particles and they are so dispersed that they occupy no volume. That's why that is valid. Okay, well, when do they not occupy any volume? And what happens as we cool a gas down? Okay, it gets smaller in volume because cool that gas further. Keeps getting colder and colder. Yes, it has less energy. Yes, they don't move as fast. So what happens? They become a liquid. Right? If we cool our temperature down so much that we can have what our particles might be considered as gases, but as we cool that down so much, they transition into a liquid. And in the liquid phase, they're now much closer to each other. The volume changes. Make sense? Okay. So that's where our temperature comes from. What's the P of STP?
Pressure.
Pressure. What is pressure? What is pressure?
Force.
It's the force your gas particles put on the outside. Yes?
So under all this, it's going to look stupid, but the whole dry ice thing, I don't even know.
We can talk about dry ice a little bit later. Doesn't quite work here because you're looking at phase transitions. So what is pressure? It's our force. So we're looking at standard pressure. When might this equation not work?
When there's no pressure.
If there's no pressure, now those particles are hitting virtually nothing. Okay, so we've got our container, the pressure is the particles pushing outwards. That's our gas. If we have no pressure, are there many gas particles?
So when there's nothing.
There'd be very few gas particles. Well, does that match no volume? If we have very few particles, is there a volume being occupied? Not really. So low pressures, this holds pretty true because there aren't really any particles there to remove volume or to remove that space. What happens if we go to high pressures? Now there's a lot more particles. Those particles now increase the likelihood of interacting with each other. Well, if they interact with each other, are they removing volume? Yes. Now that assumption becomes invalid, which then means our ideal gas expression becomes invalid. Okay? So when we're looking at our temperature and our pressures, it's recognizing why and when this becomes useful and when it fails. At low pressures, this is probably pretty darn close to true. Okay? It is still probably 1 mole of a gas equal to 22.4 liters. Okay? At really low temperatures, not true. What about really high temperatures? What are our particles doing? They're now moving around so much that it also kind of decreases the likelihood of them impacting each other. Really high temperatures and really low pressures, that equation is still probably valid. It's only when we reduce the motion by dropping the temperature or increasing the pressure that the equation becomes invalid. Okay? Or that expression becomes invalid. And what we ended with on, today's Thursday?
Yes.
What we ended with on Tuesday was that this is an equality. And what do we do with equalities? We can turn them into conversion factors. So, solve it. I want to know how many liters are needed to hold 2.0 grams of hydrogen gas. I'll give you a first hint, or the first few steps. Step one, number one, I want to know what I get for an answer. I'm trying to get to liters. What am I starting with? 2.0 grams of hydrogen gas. Answers for this guy. Where did that conversion factor come from? Periodic table. How did we calculate it? Molar mass of hydrogen was 1.01 or 1.008, which we had over here. Okay. So depending on which periodic table you used, you're going to get varying amounts of significant digits. We multiply both of those by 2. We get 2.02 or 2.016. Okay. You notice I wrote 2. Oh, son of a... Why did I write 2? This is a horrible, horrible process, actually, on my part that I should stop doing. Adding in the extra 0.2 is going to change my number how much? Tiny, tiny, tiny little bit. So little that I don't care. And on a multiple choice test, I could say whichever one was closer. Okay? And I recorded that. That was phenomenal. Okay?
But you didn't also record you need to change it.
Yeah, which is the next part. You should be reporting out as many significant digits as you possibly can. And that's then going to come down to kind of a balance. Because we could look up the mass of hydrogen online and report it out to probably 6 or 7 sig figs. How many sig figs should we use? What was our rule when looking at our conversions? When we run a calculation, we want to make sure that the number that dictates the sig figs in our answer is our measured value, not our conversions. If the conversions dictate, we're now losing accuracy from our measurement. What was our measurement? 2.0 grams, which means I need 2 sig figs, which means minimally in each of these next steps, how many sig figs do I need? I need at least 2 sig figs. Or less. I don't want to fix it. Okay? So when I write out 2, that's not perfect. Okay? If I wrote 2.0, that didn't really change it. Okay? But ideally, we would carry it to make sure that we're really covering our bases. And so we would ensure that 3 sig figs makes a little bit more sense because we have that 1 extra decimal. So on an exam, I would recommend using the 2.02. Okay? Ideally, you turn the volume down on what you're listening to, which is probably why you can't hear me. I can hear the video. Our 2.016 okay, would work. Okay? But what is that going to do when we go through and do our calculations? That's going to change our number. We're going to get a slightly different result coming out of that. That could then mess with our multiple choice exams. We want to keep our focus on our multiple choice. It's going to vary. Okay? How many of you have to move into future general chemistry classes? 151, 152. So there's a couple people. Those of you are going to need to pay very careful attention to your sig figs, unfortunately, because the rest of our general chemistry faculty are very nitpicky in sig figs. Okay, which means you need to keep track and be as careful as you can when going through and solving. Okay? Realize again, multiple choice tests, they probably aren't testing on do you know the difference between 2 versus 2.02 versus 2.016. So your multiple choice answer will probably come out darn close. Kind of make sense? Yes.
Since given value, wouldn't it is would like better if you wrote 2.0 versus 2.0?
So if we changed our molar mass to being 2.0, that gets us 2 sig figs. So minimally that matches, but we could be losing some information there possibly. So when we do our conversions, we usually want to add at least 1 extra sig fig. And it's typically only 1 extra because we keep adding, it's just we're gonna lose it anyway. So we just carry that 1 extra one to help us out with it. Okay, makes sense? We then have our 22.4 liters, set this all up. We can punch it into our calculator, and a few people got a couple different answers. We saw a 22.178, a 22.4. Everybody else just wrote down 22. Why'd you write down 22? Is that what your calculator spit out? No. This comes back to our sig figs, which I was alluding to up at the front. For some reason, you guys have been phenomenal at sig figs, much more so than I have ever been in my life. Okay, so that's a good thing on you guys. Okay, so you're paying attention to the sig figs. That's awesome. Keep with it. Hopefully that'll make sure you do well later on. Okay, so if we wrote down at least one version that has multiple digits, 22.178, we'd underline our 2 sig figs. 1 is our first insignificant digit. What's its relationship to 5? It's lower than, so I don't change it, and I get 22 liters. Make sense? So we're trying to use our conversion factors to set us up and convert our way through. When can I use this 22.4 liters per mole? When it's standard temperature and pressure. That's valid. When else? It must be a gas. Okay? So we need to be seeing those key words. If we take a look at the question, is it a gas? Yes. How do you know that? It says gas. Okay. Is it at standard temperature and pressure? It doesn't say. Okay? Which then means it's a horrible question, and you should be raising your hand and being like, dude, you wrote a crappy question. Are you saying we're at standard temperature and pressure? Okay. And then that's when I would say, yes, do it that way, because I don't want to come up with other numbers. Okay. You should not always assume, because sometimes you're given the information buried somewhere else. Okay. So you should make sure it is clearly stated. Okay. If you move into a future class and they aren't clearly stating it, you need to ask them and be irritatingly annoying and be like, you didn't specify, I don't know how to solve this. Okay. Which is why I think other chemistry instructors get pissed at me. I tell students to be specific. Okay? So here's another one. How many liters of hydrogen are produced from the reaction of 0.165 grams of aluminum metal when it is reacted with dilute hydrochloric acid? Okay, you remember the molarity question that we went through and solved? Vaguely? Guess what we're doing in this one? Same process. I'll give you 5 minutes to try and put something together with this. If you've got questions, I'll come to you. Okay? Get as far as you can within this question. What's your...
Can I use some notes I took on my phone from the tutoring lab?
Yeah, absolutely. Use as many notes as you want. Okay. What's a big piece of information that we might need on this? Balanced equation will be helpful. What else do we need?
It's also a single replacement.
It is a single replacement. What was said in the back? Is it at standard temperature and pressure? Okay. It's not specified. We don't know, which then means this question becomes not possible to solve. So, it's at STP. Okay. You are at standard temperature and pressure.